line in the xy plane where y equals 1 and the line in the yz plane where z equals 2, right? So you're right. If it didn't say in the plane, it would be a plane, and then you're like, that makes no sense. But here you go. This right here is y equals 1, right? And then this one right here is z equals 2. So how do you go about forming that formula then? How do you go about that? Is you're talking about finding this equation right here? And that line is independent of x, right? So all you really need is that coordinate right there. If you did it in terms of y, like what point? Well, I'll do it in 3 space. What point is that? That's 0, 0. What is that? 0, 0, 2, right? And then it goes to the point what? 0, 1, 0, right? Exactly. So what is that equation in terms of? That's z equals negative what? We're doing this in terms of y. Negative what? 2y plus what? It's negative 2y plus 2, right? It doesn't depend on x, so therefore, guess what you have right there? The plane. You have the plane right there. This right here, you see this right here? On the plane, that's this line right here. Correct? But then once you put it in 3 space, there's no x value, so therefore it's going to go forward and backward. Yeah. It's a 3D extension of a 2D construct. Yeah. Cool. Of a plane. What did we have? Z equals what? Z naught plus mx minus x naught, right? Plus n and y minus what? Y naught. And what do we know m is equal to dz what? Dz dx. Remember we made the eyeball. Okay, I'm going to say we here because we made the mistake. N is equal to dz dy, right? So if you look at the chart, so the only thing that you should have consistent are the m and the n, right? So you can look at the chart, and what can you find immediately? What's the change in x? So the change in x is when you keep y the same. Every time x goes up by 1, what does z go up by? 2. And on this one, every time you keep x the same, what does y go up by? It goes down by what? A half, right? So then I think, Tori, you asked the question, depending on what initial point you pick, is absolutely, this is just like parametric. You can anchor the point, and you're going off in the right directions. You're like a line starting here going back and forth is the same thing as a line starting here going back and forth in the same vector direction, right? So you could pick any point you want. You just need to pick a point. It depends on what. 0, 0, 1, yeah. So you could say 0, 0, 1. Right, exactly. That's just a nice point because it has 2 zeros in it. Well, hold on. Let's see what happens. Hold on a second, James. Let's see what happens. So if we actually do this out, we're going to end up with z is equal to what? 1 plus m, which is 2 times x minus what? 0. Not plus, minus what? Minus a half times what? Y minus 0. So you end up with z is equal to 1 plus 2x minus what? 1/2 y. Okay. So I think, Tori, the question you're asking is if we picked a different initial point, will we end up with the same equation?
I had that, yes. Especially for number 1.
Okay, well, let's just check this one for a second. Let's just check this one. On the graph here, how about 1 is x, 1, 2, 2 is a point on here, okay? 1, 2, 2 is also a point. 1, 2, 2, right? Yeah. 1, 2, 2 is a point, yes. 1, 2, 2. I can't say, every time you say something multiple times, it doesn't work yet. So hold on. So 2 is equal to what? Z is equal, Z is equal to, Z is equal to 2 plus, the m is still the same, right? 2 times x minus 2 plus x minus 1. Thank you. That was a mistake. X minus 1 minus a half times what? Y minus what? 2. So let's clean this up and see what happens. And again, we're back in algebra. So they might not look exactly the same at the beginning, but they should come out to be the same. Yes? Functions in 3 variables. We've looked at functions in 3 variables. And what was the way we looked at a function in 3 variables but projected onto 2 variables? What did we do? We drew a family of what? Yeah, so we had 3 variables, right? But then we looked at it in 2 space using what? Contour diagrams, right? Okay. So what essentially we're going to do now is we're going to say what happens if we had 4 variables. We can't really graph that too well. It kind of gets a little bit complicated. But contour diagrams in 2 space, you can do the same thing in 3 space. So maybe instead of concentric circles for a cone or spaced out for some bowl, what we're going to have instead are contour diagrams in 3 space. Now, are we going to ever be graphing these by hand? No. This is just another layer. This is just another layer of spatial reasoning. That's it. Okay? We're not doing anything. You're not going to be sketching like Da Vinci, okay? Because it's really hard. So what you see this. A level surface or level set of a function of 3 variables is a surface of the form f of x, y, z equals some constant. F of x, y, z equals some constant. You take x, y, and z and it equals a constant. The function f can be represented by a family of level surfaces allowing C to vary. So how did we draw contour diagrams from 3 space down to 2? We picked a constant, drew the thing, picked another constant, drew the thing, and we sketched it on a plane. Well, can you draw 3-dimensional surfaces? Yeah, for example, what's x squared plus y squared plus z squared equals 1? What is that? That's a sphere of radius around what point? The origin, exactly, right, exactly. So for example, let's say you're thinking about a planet. You could theoretically want to know what the temperature is at a specific point in 3 space, right? So here's a 4-dimensional function, right? This point in space has a certain temperature. To describe this point in space, how many numbers do you need? 3. You need 3 numbers. But then you're assigning a value to that position. The position is three things. The temperature is or the color, whatever you want to call it, is a 4th, right? So what we can actually do here, so let's say they define it, they give you a temperature. So this is what it looks like here. So, let me turn off the light so you can actually see it. So do you see what's going on there? It's also, a slice is cut out of this so you can see what's going on. So you have concentric, not concentric circles, you have concentric what? You have concentric spheres. So what is this telling you? As you get further from the center of this, let's call it a planet, what happens to the temperature? No, it's getting higher and higher and higher. It's because the temperature is defined as x squared plus y squared plus z squared. Yes?
And we could go as many steps through this as we
absolutely,
want.
Absolutely. So remember how we drew some curve. Remember when we first saw surfaces in 3 space? It was points in space and connected with like a lattice. The more points you took, the smoother the surface could be. Yeah, you could take more and more, but does this get busy real quick? Oh yeah, absolutely. But the idea is this is just another way to visualize 3-dimensional, actually 4-dimensional data. You have three points for position and 1 point for temperature. Could it be color or acidity or charge? It could be something, right? Exactly. It's pretty cool. There's no z, right? So x squared plus y squared, those are all circles on the xy plane. But if there's no z, what does that mean? It turns into a what? Instead of a circle, it turns into a cylinder, right? So as you vary this, as you vary x squared plus y squared equals 1, x squared plus y squared equals 2, what do you end up with? Lots of concentric what? Cylinders. You end up with lots of concentric cylinders. Yeah, you end up with lots of concentric cylinders. What about this one right here? Similar situation. We have gxyz equals z minus y. What's missing from there? The x, right? The x. So you could graph this in the yz plane. Where's the yz plane? It's really hard to see right there. The yz plane is right here. It's kind of behind there, the yz plane. So if you looked at where these cross the yz plane, you would get lots of parallel lines, right? You'd get all these parallel lines where these cross. But then, since there's no x in it, what that line turns into a plane. It moves forward and backward. So all you're essentially doing is looking at 3-dimensional contour diagrams. There's nothing else. This is a direct extension of 2-dimensional contour diagrams. It's a direct extension. So the homework tonight, there's no new material I have to show you. You're going to just actually start thinking more about these 3-space constructs and how they fit together. Now, the last thing I'll leave you with is there is a page in your book that's really important. Ray asked me if he needed to memorize it. My immediate response is no, you don't have to memorize it, although it would probably help you to have a very good idea about each of them. There's a catalog of surfaces. It's on page 671 in your book. Let's see, I can't really bring it up on that. Well, actually, you remember when remember graphing by transformation? You know, you would say, like, you would know that y equals x squared looks like a parabola up, right? We talked about this a little bit. You could make all these transformations. You could say y is equal to x minus 2 squared. That means the graph goes 2 to which direction? It goes 2 to the right. Does it change shape? No, it doesn't. So similarly, if you can remember what these look like and the families that they come from, it's easier to come up with a general idea of what's going on. But yeah, it's 9 things. It's a little bit annoying. There's certain ones that are more common than others. And again, which one's my favorite? Yeah, the hyperbolic paraboloid. Yeah, I like it a lot.